Okay, what we're going to look at today is speed time graphs. So again, you have talked about speed time graphs before, so you know about them from second year. So speed time graphs, basically, they're quite handy because they can show you what speed something's traveling at a certain time. So if you wanted to know what speed a car was going at 30 seconds into its journey, you could look at the graph and work it out. Okay, so stationary objects. Now, stationary object just has 0 meters per second. It's not traveling, so it would just be a line along the bottom like that at 0. If an object's speeding up, it would look like that. So it's increasing speed every certain amount of time. So if you went 1 second, it would be that speed. The next second, it would be a higher speed. Slowing down is the opposite. So it starts off at higher speed and decreases. It doesn't always have to end at 0. And number 5, object moving with a constant speed. That means it's the same speed constantly. So it might be 10 meters per second, for example. It would just be 10 all the way along. Hopefully you remember that. So, example. Speed time graphs can be used to monitor the speed of an object during its journey, calculate the distance travelled by an object during its journey, using distance as average speed times time, or calculate the acceleration of an object. So, we've got a graph here. We can see that it's speeding up, then it's a constant speed at B, then it's decreasing its speed, so it's slowing down at C. So section A, object has constant or uniform positive acceleration. Since the line is straight, the average speed during section A is, to work out the average speed, what you need to do with a straight line is you've got 2 points that you know the final and you know the initial. So if you know 2 points, to find the average of those 2 points, what do? You add them up and you divide them by how many points there are to find the average. And that's obviously 20 plus 0 divided by 2 is 10. So it's midway between the 2 points. The distance travelled during section A is the average speed, has to be the average speed, times by the time. And the time is 20 seconds. So 200 meters. So the speed of the object increases by, it goes from 0 to 20, so it increases in 20 seconds by 1 meters per second every second. So every second it increases 1 more until it finally gets to 20 in 20 seconds. Section B, constant speed. The average speed is just the speed that it's travelling at, because it'd be 20 plus 20 plus 20 divided by 3 or whatever. And the distance travelled is the average speed times by the time, so 15. And that comes to 300 meters. Section C, the constant or uniform negative acceleration. The average speed, so we've got 2 speeds, we've got that one and we've got that one. So 20 and 0, so 20 plus 0 divided by 2, which is 10. So the average speed is 10 again. The distance travelled is the average speed times by the time. So it's only got 10 seconds, so it's 10 times 10, which is 100 meters. And the speed of the object, so it decreases by a certain meter per second every second, where it takes 10 seconds to decrease 20. So it must be decreasing by 2 meters per second every second. Okay, so we know we can work out the distance doing the average speed times the time. That's a bit of a long way around because you have to then find the average speed first of all. A quicker way to do it is actually find the area underneath the graph. So let's look back at section A again. So this section here. Okay, so by the area underneath the graph, I mean that area there that I'm hatching. So in section A, if we wanted to know how far it has travelled, you find the area under the graph. So the area under that graph is a triangle. So the area of a triangle is half times base times height. So half times 20 times 20, which is 200 meters. So they're the same. You can do that with any speed time graph. So note, whatever the shape of the speed time graph, the distance travelled, and everyone forgets this and it's a really easy way to do things, is the area under the speed time graph. And acceleration is calculated from the steepness or gradient of the graph. So worked example. The car accelerates uniformly from rest to a speed of 30 meters per second in 15 seconds. It then remains at 30 meters per second for 20 seconds. And then the car decelerates uniformly to rest in 5 seconds. First of all, sketch a speed time graph to represent the whole journey. So we've got the increasing, a bit of a misprint there, that should be 30, increasing to 30 meters per second in 15 seconds. Then we've got the constant speed for 20 seconds, and then we've got it decelerating in 5 seconds. B, calculate the initial acceleration of the car. So we're looking at this part here, the part B. So remember, acceleration is final speed minus initial speed divided by time taken. So you can find the final speed from the graph, which is 30, minus the initial speed, which is 0, divided by the time it takes to go that distance, which is 15 seconds. So that comes to 2 meters per second. See the final acceleration. So we're looking at this part now, the end bit. So the final speed, it goes down to 0. The initial speed is 30, and it takes 5 seconds to do that. So that comes to minus 6 meters per second squared. D, what is the total distance travelled by the car? So you can find the area under the speed time graph. So we've got 3 blocks, distinct blocks we have to find the area of. We've got that one, we've got this one, and then we've got this one. So we've got a triangle, a rectangle, and another triangle. So the first triangle, half times base times height, so half times 15 times 30, plus the rectangle, which is 20 times 30, it's just reading off the graph. And then the triangle at the end is half times 5 times 30. And add those up, you get to 900 meters. It's a really, really good shortcut way to remember it. So you must remember that. A lot of people just forget you can do that. And the average speed of the car is the total distance travelled divided by the total time taken. So we just worked out the total distance. Total time is the entire time from the graph, so all the way along to 40. So distance divided by time is 900 divided by 40, which is 22.5 meters per second. One more example, then I'm going to get you guys to have a go. The graph below represents the motion of a vehicle accelerating from 10 meters per second to 40 meters per second in 5 seconds, and then decelerating to rest in a further 20 seconds. So the distance travelled would be the area under the graph. So now we've got a slightly different graph. It doesn't start from 0, but it's still the same kind of thing. So we need to work out what that area is, then that area, then this big area here. Okay, again, misprint there, they should be 14, 10. So distance travelled, area under the graph. So we've got 5 times 10, which is this one here. Then we've got half times 5 times 30, because that's 30 there. It's that one. And then we've got that final one, half times 20 times 40, which is this one here. And the average speed would be the total distance divided by the total time. So 525 we just worked out, divided by the total time, which is 25. So that will come to 21 meters per second. Okay, so I'm going to get you guys to have a go at some of these. As always, answers will be provided, but any questions, please let me know.